Hi folks, Mr. Long here. I'm going to do a screencast today about Newton's law of cooling, and specifically we're going to look at how a forensic person with the police, for example, would determine the time of death after they arrived at a crime scene for a murder. So kind of a morbid topic, but really truly an interesting application of exponential growth and decay. So here's our problem. We've got our descriptor right here, right? So someone was arriving at a crime scene at 7 p.m. And then what they do is they take a temperature reading of the victim and they find out it's 25 degrees Celsius. Okay, so 25 degrees Celsius. They take a second reading at 10 p.m. and it's down to 21. The room is a constant 18 degrees Celsius. And these things are all important. The other thing that we need to know about is that the regular body temperature is 37.1. So unless someone is sick, the regular body temperature is 37.1. So we've got all that information. I think the first thing you need to do is put it on a graph. So what I'm going to suggest is that we make 7 p.m. times 0. Okay, so 7 p.m. is going to be times 0. So I've got my cooling curve there, if you will. So 7 p.m. is times 0. And then that means that, let's see, the next reading was taken at 10 p.m. So at 10 p.m., right here, that's 3 hours later. Okay, and what are those two temperatures? Well, we know that the first temperature was 25 and the second one was 25 and 21. So 25 degrees, 21 degrees. The other thing we know is that the asymptote's going to be at 18 because that's the room temperature. Okay, so we have all of that information right there. We have enough information there to figure out the equation of the curve. Now, ultimately, what I'm going to be doing is I'm going to go back in time, right, from time 0 to get when that temperature was 37.1. And that will tell me how many hours the crime occurred, or the time of death occurred, before we took that first temperature. Okay, so that's our scenario. So we've got two ordered pairs, one of them at 0 and 25, a second one at 2 and 21, and we've got an asymptote at 18. So our equations for this are y equals ae to the kx plus q. And we know a few things. A is the amount of temperature that can actually decay. So if we look at it, according to this, it's the distance from that the amount of temperature that can decay out of that 25 is 7 because it can only decay as far as 18. So we know that the A value is going to be 7. So that's the distance from 18, the horizontal asymptote, up to 25, the initial temperature. So A is going to be worth 7. Then we know that it's e to the k. In this case, it'll be t. So we don't know, t is a variable. K is the rate constant. We're really not sure about that. Plus q. Q is always a horizontal asymptote. So that is 18. By the way, if you're hearing some noises, I've got a dog here right beside me that's chewing on a toy. So anyway, so my apologies if you hear some background noise. Okay, so that's our equation right there, 7e to the kt plus 18. Now, what we know is we used the 0 and the 25 here. They were used to get this equation, but we can use the 2 and 21 to figure out k. So let's go down below to see where I've already set it all up for you. So here's our equation, a times e to the tk, and sorry about the spacing. I've set it up in a spreadsheet so that it's easier to do. And then plus q is the y value that we know, right? There's a formula right there up above. And so what I did is I substituted everything in. So I know that 7 is the a value multiplied by e. And then what I did is it's t times k, right? But t times k can be written as is K times T, because in this case, I know that the time is 3 hours. So we're going to use that 10 p.m. measurement. So I'm subbing in this 3 because I'm substituting in the time and the temperature at 10 p.m. to figure out K. Right, and then I added in the horizontal asymptote Q, and I know the Y value at 10 p.m. is 21. So then I just go through inverse operations. First thing I do is subtract 18 from both sides, and that gets rid of that, and it will make that 21, 3. So I go down to the next line, which is right here. So there's the next line right there. 7 times e to the 3k equals 3. Next inverse operation is to divide by 7. Sorry, up here I guess we subtracted 18. And then I take the ln of both sides. And when I do that, when I take the ln of both sides, I'm just going to it gets rid of e, so I just have 3k equals the ln of that value. So that's my next equation right here. And then I divide both sides by 3 to get the k value. And so now I actually have an equation. Y equals 7e to the negative 0.2824t plus 18. Okay, so that's the first thing. So I need to get k. I need to have an equation. Before I can figure out when the time of death occurs, I needed an equation. So I've got my equation. Now I need to I need to use that equation to figure out the time of death. So let's go into this next part where I'm getting the time of death. So there's my equation right here. So you can see that that's my equation right there. And I need to solve for T. And I'm setting the temperature equal to 37.1 because that was the temperature at the time of death, right? That's what the average person's body temperature is. And then it only starts to cool after the time of death. Okay, so first thing I'm going to do is subtract 18 off both sides. Process is very similar to last time. And then I need to divide by that 7 right here, right? I have to get rid of that 7. And then I have this e to the negative 0.2824t. So I've got to do the ln of both sides. And then I get negative 0.2824 times t. Sorry, that's not this thing here. It's not. It should be at the same level vertically. So that equals 1. And then I divide both sides by that negative 0.2824, and I end up with this t value, which means the murder occurred about 3.5 hours before 7 p.m. Which is, well, 3 hours before 7 p.m. is 4 p.m. So it's about around 3:30 p.m. approximately. Okay, so that would really, in terms of understanding the crime and solving a crime, it's quite helpful to know that the death occurred at 3:30 p.m. So again, I'll go over that, just a quick summary of that. So what we did is we had a problem where we knew police arrived on a crime scene. They did 2 temperatures at 2 different times, and they know what the temperature of the room is, right? And it's usually a constant. And then they know what normal body temperature is. So you have to come up with an equation. And the equation for Newton's law of cooling is this one right here. So when we go through this, it's easy to figure out A, because A is the amount of temperature that can decay. So when they first measured temperature, it was 25, and they know that the room temperature is 18, so the maximum amount of change is that 7. And then again, there's the asymptote 18. So after that, really, we've got both K and T as unknowns, right? And so we have to figure out, before we can figure out when the crime occurred, we have to figure out, okay, that rate constant. And we do that by substituting in this ordered pair of 2 and 21. So that allows me in this step here to get the rate constant. Once I have the rate constant, then I have my overall equation. And now I can use the equation to get a temperature at any time or a time at any temperature. So, and then only at this point do I set the temperature equal to that 37.1 and solve for T, which would be the time of death, because that's when the temperature started to decrease, right? So it was 37.1 until that specific point in time, and then it started to decrease. So that's when we know it's the time of death. Okay, so hopefully that helps. And there's going to be a question like this on your mastery test. So again, you may want to go over it. You may want to try it, close it up and try it on your own. There's a variety of things, or come and see me for extra help if you need it.